In this section, we'll look at implicit differentiation. Implicit differentiation allows us to take graphs that are not the graphs of functions and find the slope of the tangent line to points on these graphs that are not functions. Let's look at this example. This is an example of a graph that is not a function. This particular curve dates back to Descartes in 1638. It's called a folium. Although it is not a function, it fails the vertical line test. If we divide it into 3 separate pieces, as you see the pieces here in yellow, pink, and blue, each one of those pieces by itself is a function. So we're going to be looking at what we can do if we have graphs that are not the graphs of functions, graphs that fail that vertical line test. Let's start with this graph. Y squared equals x. This is not a function because for a particular x value, so for example x is 4, then there's 2 different y values that could generate an x of 4. 2 squared is 4 and negative 2 squared is 4. So this is not a function because I have one specific x, 4, that can have 2 different y's. The graph is a parabola, and it's a parabola that is on its side, and so it has a graph that looks something like this. It's not a great graph, but it has that kind of a shape, and it is going to fail our vertical line test. So this is not the graph of a function. Now what we can do if we want to find the derivative explicitly, the way we have been finding these, is we can solve for y. Now if we have y squared equals x, and we solve for y, we can get rid of the square by taking the square root of both sides. Remember when we do that, though, that we have to include plus or minus, because like with our example before, you could have 2 different values that will squared give you the same x value. So like for 4, you could have 2 squared or negative 2 squared. So we have to include the plus or minus. Now what we can do is we can say we have 2 y's. We'll call y1 the square root of x and y2 negative square root of x. When I look at this graph, the graph that's at the top is the square root of x, and the graph at the bottom is y equals negative square root of x. So this equation is actually these 2 functions put together. Now if we want to find the derivative of y1, we'll need to remember that the square root of x is actually x to the 1/2 power. Then we can apply the power rule, and that's 1/2 x to the negative 1/2. In order to apply the rules to y2, we need to remember the constant multiple rule, which says this is negative 1, and then again it's negative x to the 1/2. So when I bring the 1/2 in front, I'll have negative 1/2 x to the negative 1/2. So depending on whether your point is a point that's along the top portion of the graph or along the bottom portion of the graph tells us which one of these formulas that we would use. Notice if I were along the top portion of the graph and I drew a tangent line, it would have a positive slope. And if I were along the bottom portion of this graph and I drew a tangent line, I would have a negative slope. And here is a much better picture than what I drew, obviously. It shows you graphs, and it shows the slope of a tangent line at a particular point for each one of those. And again, you'll notice it has positive slopes when we look at the top part of the graph, and it has negative slopes when we look at the bottom part of the graph. What we want to do is we want to use implicit differentiation so that we can deal with graphs that are not the graph of functions. What we have to do is differentiate both sides of the equation with respect to x. And we have to treat y as a differentiable function of x. Then we're going to collect the terms with dy dx on one side of the equation. Now, some people prefer to use dy dx. Some people will prefer to use y prime. Sometimes it's easier to use that notation than to use dy dx. And then once we collect the terms with dy dx on one side, we are going to solve for dy dx or solve for y prime. Now we are given this graph, x squared plus y squared equals 25. This is the graph of a circle with the center at the origin and a radius of 5, so that we can visualize, and we know of course that a circle is not the graph of a function. When we differentiate this, we start and we differentiate each term. So we are going to take the derivative with respect to x of x squared, plus we'll take the derivative with respect to x of y squared, and then we'll take the derivative with respect to x of 25. Now the derivative with respect to x of x squared, remember we make the 2 a coefficient, will be 2x. Now we are taking the derivative here with respect to x, and what we have is a y. When we take the derivative with respect to x, we will take and use the power rule first, which is 2y. But since we're taking the derivative with respect to x, we will need to multiply this by dy dx. And the reason this is a part of the chain rule, and remember with the chain rule, we took the derivative of the function, outside function, times the derivative of the inside function, and the inside function is y. Next, we look and we take the derivative of 25, which is a constant, and will be 0. Now we are solving for dy dx, and we treat this just like we would any other linear equation. We will move our 2x over by subtracting 2x from both sides. So we will leave the 2y dy dx on the left, and we'll subtract 2x from both sides, which leaves us negative 2x on the other side. Now we are solving for dy dx, so we need to get rid of the 2y, which is being multiplied. So we will divide both sides by 2y. That will give us dy dx equals negative 2x divided by 2y. This, of course, can be simplified since I have a 2 on top and bottom. So dy dx will be equal to negative x over y. Now the only difference I was talking about with the notation is that instead of dy dx, you can use the y prime notation. Some people find that easier than using this fraction through their entire problem. And the only difference is you would have y prime equals negative x over y. Now here is the graph we were just looking at, the equation of x squared plus y squared equals 25, and you can see it's been broken down into 2 pieces. Here's a function on top and a function on bottom. Now if we want to find the tangent line here at 3, negative 4, then we will just plug in to that formula we found, dy dx equals negative x over y. And so dy dx at the point 3, negative 4 is equal to negative, and we plug in our x is 3, over y, which is negative 4. Negative divided by negative is positive, and we'll have a slope of positive 3/4. Now notice I had to know the x and the y. Since this is not a function, there's also a point up here that will be 3, positive 4. And so I have to know not only the x, but also the y to be able to find the slope at the point. Because while this slope is positive, if you think about the tangent slope here, my picture's not great there, but if you think about the tangent slope here, it will be negative. It will have a negative slope. Now one more example. Let's take this equation, x cubed plus y cubed minus 9xy equals 0, and let's take its derivative using this implicit differentiation. Obviously this is not something that I can solve for y. In order to be able to use the rules that we've used in previous sections, you would have to be able to solve this for y easily, and you'd have to be able to solve for y and get one formula, as opposed to like the circle or the parabola we just looked at that was actually 2 different pieces. So what we'd have to do here to take the derivative is we would need to go through and take the derivative with respect to x of x cubed plus the derivative with respect to x of y cubed minus the derivative with respect to x of 9xy, and that would be equal to the derivative with respect to x of 0. Now if I look at this one, this is with respect to x, and we have x here, so we just bring this out. This is 3x squared. Now since this is y, we will do the same thing. We'll do 3y squared, but we have to multiply by the derivative of y. And I'm going to use y prime this time, just because I think it's easier to use than dy dx. Now when we find this derivative, notice that it is a product rule. So we're going to have to apply the product rule here, which says we take 9x times the derivative of y plus y times the derivative of 9x. And this is all equal to the derivative of 0, and since 0 is a constant, we know that derivative is 0. So we'll have 3x squared plus 3y squared y prime. Now here the derivative of y would be 1, but we also have to take the derivative of y, which is y prime. So we'll have minus 9x y prime. Now notice the minus, we'll have to distribute it through here. The derivative of 9x is 9, so we'll have y times 9 is 9y equals 0. Now, our next step is to solve for y, and in order to do that, we need to keep the y prime terms together, and we need to move the other two terms to the other side. So I'm going to keep the 3y squared y prime minus 9x y prime on one side. On the other side, if I move over the 3x squared, if I subtract it and I add the 9y to both sides, I'll have positive 9y on the other side minus 3x squared on the other side. Now notice I have two y primes. I'm trying to solve for y prime. If you have two different terms that have the same variable you're trying to solve for, factor it out. Y prime times 3y squared and y prime times negative 9x. And then we will divide both sides by what we have in parentheses here. And that will give us 9y minus 3x squared divided by 3y squared minus 9x. Now you should note that this is not in the simplest form possible, since the top and bottom all have a common factor. So if I will factor out the 3, this will be 3y minus x squared. If I factor out the 3 on bottom, I'll have y squared minus 3x. Cancel my 3's, and the simplest form for this derivative is 3y minus x squared divided by y squared minus 3x. And you'll notice again, you have to know your x and your y both to be able to find the derivative of this function, or of this graph. One other thing I want to remind you of, first here's the picture. Again, if we want to find equations of lines that are tangent or normal, either one to this curve, to find the tangent, we would plug in the point 2 for x and 4 for y into our equation. If we want to find the normal line, remember that that is perpendicular to the tangent, so it will have the opposite reciprocal slope. So whatever you get when you plug in 2, 4 into your y prime equation, take the opposite sign and the reciprocal, and that will give you the slope for the normal line.